Traffic signals across the northern districts failed simultaneously, leaving intersections locked in dark silence, while the rest of the city continued operating normally. Power engineers initially suspected a substation malfunction, yet grid telemetry revealed a pattern no equipment fault could produce. The outage formed a near-perfect circle across several square kilometers of dense urban infrastructure. Electrical current had vanished only inside that boundary, while every transmission line feeding it remained fully energized. The shape appeared first during a routine overnight stability review of the municipal grid control system. Operators monitor load distribution continuously, looking for minor deviations that could signal equipment fatigue or transformer overload. Instead, the display presented a symmetrical absence. Entire neighborhoods were drawing no power at all. Yet every feeder cable leading into the region showed normal voltage. Electricity had simply stopped existing within the circle. Emergency dispatch initially treated the event as a localized blackout. Field technicians were sent to inspect distribution nodes along the perimeter streets. They arrived expecting tripped breakers or damaged transformers. They found streetlights functioning normally on the outside edge of the district. One step farther inward, the lamps were completely dark. The contrast formed a sharp electrical boundary running through sidewalks, parking lots, and apartment corridors. A technician standing on the threshold of the outage tested a lamp post using a portable meter. Voltage measured normally on the supply cable feeding the pole. The internal circuitry registered full input potential. But the lamp itself produced no light. Replacing the bulb changed nothing. Installing an entirely new fixture produced the same result. Electricity was reaching the device, yet illumination never occurred. The technician repeated the test on multiple posts along the boundary street. Every result matched. Voltage present, electrical function absent. By early morning, the utilities grid analysis team began mapping the affected region using feeder load data. The outline gradually emerged as thousands of individual consumption points dropped to zero. Homes, shops, traffic infrastructure, telecommunications cabinets, every device inside the region behaved identically. Power entered the buildings through underground cables. None of it performed work. Electric motors failed to rotate. Heating elements remained cold. Computers refused to start. Even simple resistive devices such as incandescent bulbs produced no glow. Outside the boundary, everything functioned normally. The circle measured slightly more than 2 kilometers in diameter. What unsettled the engineering team most was the precision of the edge. Power lines did not lose voltage when crossing into the area. Instead, the electrical behavior of the connected equipment changed the moment it physically existed inside the region. A transformer positioned just outside the perimeter delivered full output to distribution cables running beneath the streets. Meters inside nearby apartment buildings recorded incoming voltage. But nothing inside those apartments consumed power. Engineers initially suspected a measurement artifact, an unusual interaction between smart meters and the supervisory grid software. A secondary verification was ordered using portable diagnostic equipment carried directly into the district. The results matched the digital readings exactly. Electric potential existed throughout the network. Energy transfer had ceased. That distinction required careful explanation during the morning briefing. Electrical power systems operate through the movement of charge performing work inside devices. In this case, charge movement appeared unaffected. The potential difference remained measurable. Conductive pathways remained intact. Yet devices behaved as though electrical current had lost the ability to interact with matter. An electrical heater inside a maintenance van provided a striking example. When the vehicle was parked just outside the boundary, the heater operated normally. The van moved slowly into the dark district while engineers monitored the device. The heater element continued receiving current. The metal never warmed. A few meters deeper into the region, the current itself disappeared from the instrument display, even though the supply cable feeding the van remained energized. The behavior suggested that electrical interactions with conductive materials had been altered locally. The infrastructure supplying power had not failed. The physics of electricity inside the district had changed. City officials authorized an expanded inspection zone by late morning. Police closed several streets after traffic signals inside the circle proved unreliable. Hospitals within the area switched to emergency generators positioned just outside the perimeter, running temporary cables through windows. The generators produced electricity normally. The power ceased functioning once the cables crossed the boundary. Engineers extended those cables through long conduits reaching deeper into buildings. The result never changed. The equipment inside the district refused to convert electrical energy into motion, heat, or light. One particularly revealing experiment occurred at a municipal maintenance depot near the center of the region. Mechanics pushed a portable generator into the building itself. The generator continued producing voltage at its terminals. Devices plugged directly into the generator failed to operate. Moving the generator back outside, the building instantly restored their function. Electricity existed. It simply could not behave normally within the circular zone. This observation redirected the investigation toward environmental causes. Atmospheric interference sometimes disrupts radio signals, but electrical conduction in solid materials normally remains unaffected. Engineers began scanning for electromagnetic disturbances, ground conductivity anomalies, and temperature gradients that might alter component behavior. The surrounding environment appeared entirely ordinary. The city's satellite monitoring systems provided another layer of verification. Infrared imagery taken during the morning showed a subtle thermal contrast across the district. Buildings inside the circle cooled gradually as heating systems stopped functioning. More surprising was what appeared along the perimeter. A narrow ring roughly 5 meters wide displayed slightly elevated ground temperature relative to surrounding streets. No known grid component existed along that line. Electrical mapping continued throughout the afternoon. The grid's load distribution software produced the most detailed view of the anomaly yet. Every power-consuming device inside the region had effectively become an open circuit. Electrical potential remained present, but energy conversion processes failed entirely. One analyst proposed that certain materials within devices might have undergone a change affecting electron behavior, something similar to a large-scale alteration in conductivity or resistance. The hypothesis collapsed quickly. Copper wires inside the zone still conducted electricity. Measurement probes inserted into circuits confirmed that charge could move along the conductors. The problem occurred when that electrical energy attempted to perform work. Heating elements stayed cold, motors refused to spin, electronic circuits remained inactive. Electrical energy was present, but had lost the ability to interact with matter. This distinction triggered a second, more troubling discovery. Engineers monitoring the grid noticed that the circle's boundary had shifted slightly since the initial detection. The center remained roughly consistent, but the perimeter expanded outward by approximately 40 meters during the afternoon. The change occurred slowly enough that it escaped immediate attention in the early data. Once plotted across several hours of readings, the motion became clear. The district, without functioning electricity, was growing. Field technicians confirmed the shift while testing streetlights near the southern edge. Lamps that had been operating earlier in the day were now dark. Replacement bulbs produced the same result observed elsewhere. Electrical devices had crossed into the region where electricity no longer behaved normally. City engineers began installing monitoring equipment along the perimeter to track the boundary's movement more precisely. Portable generators, resistive test loads, and diagnostic sensors were placed at measured intervals. Most devices produced identical readings: voltage present, no functional energy transfer. But one experiment introduced a new pattern that investigators had not anticipated. A high-capacity mobile transformer was positioned just outside the expanding boundary and connected to a cluster of diagnostic loads placed inside the zone. Engineers intended to measure how the anomaly interacted with large-scale electrical equipment. As the circle expanded toward the transformer's location, technicians prepared to move the equipment away from the perimeter. The shift occurred sooner than expected. When the boundary reached the transformer's position, the equipment continued operating normally for nearly 2 minutes. Then the transformer output dropped to zero. Inspection revealed that the device itself had not failed. Its internal electrical components now behaved exactly like every other device inside the district. The anomaly had not merely affected the equipment. The transformer had become part of the altered electrical environment. The circle had replaced the way electricity interacted with matter across everything it encompassed. And by nightfall, the expanding boundary had reached the outer edge of the city's primary power corridor, an underground transmission route supplying electricity to several surrounding districts. The grid infrastructure approaching that corridor carried enough power to supply hundreds of thousands of homes. If the circle continued expanding, the electrical behavior of that transmission line would eventually change as well. And no engineer could explain what would happen when the city's largest power artery entered a region where electricity no longer performed work. The underground transmission corridor lay less than 400 meters beyond the southern edge of the expanding zone. 3 high-capacity cables ran through a reinforced concrete conduit beneath an industrial boulevard, carrying a substantial portion of the region's electrical supply into the city center. Under normal conditions, the corridor operated far below its maximum thermal limit. The infrastructure had been built with redundancy. But no design standard accounted for a situation in which electricity could enter a cable and then lose the ability to perform work inside the material itself. Utility engineers gathered in the control center as the monitoring equipment along the perimeter continued transmitting measurements. The circle's expansion had slowed during the evening hours, creating a temporary impression of stabilization. Several analysts argued that the growth might stop entirely. That assumption lasted until the next set of field readings arrived. Portable load banks positioned along the southern streets began reporting the familiar pattern: measurable voltage present, but no resulting energy conversion. Lamps placed inside the devices remained dark despite receiving electrical potential through the supply lines. The boundary had moved again. Police patrols extended the restricted zone while technicians repositioned diagnostic equipment along a wider ring around the district. Streetlights on the outer perimeter continued functioning normally, illuminating a sharply defined boundary where darkness resumed. Drivers crossing that line could watch illuminated storefronts vanish into unlit buildings within a single block. Electrical engineers focused their attention on the underground transmission corridor. The conduit contained cables designed to handle enormous current flows with minimal resistance. If the anomaly altered how those cables interacted with electrical energy, the consequences would extend far beyond the original district. Grid operators began redistributing regional load through alternative routes to reduce dependency on the corridor. That precaution proved necessary sooner than expected. Sometime after midnight, a sequence of routine thermal readings from the cable corridor revealed an irregular pattern. The cables were still energized and carrying current, yet their temperature remained lower than predicted by standard operating models. Ordinarily, electrical current passing through copper conductors generates measurable heat as energy interacts with the material lattice. The cooling trend suggested that this interaction was weakening. The circle had reached the outer boundary of the conduit. Field crews stationed nearby confirmed the transition using handheld equipment. Voltage measurements along the cable shielding remained normal. Current readings were stable. Yet thermal sensors embedded in the conduit walls recorded almost no heat output. Electricity was flowing, but it was no longer transferring energy into the surrounding material. Operators initiated a controlled reduction of current through the corridor to avoid unpredictable behavior. Power was diverted through parallel transmission routes serving the outer districts. The maneuver prevented an immediate grid imbalance, but created a second complication. Large portions of the city were now relying on electrical paths that had not been designed to carry sustained peak demand. The anomaly inside the circle had effectively rewritten the electrical properties of everything it touched, including the largest conductors feeding the urban grid. By early morning, the perimeter monitoring stations revealed another change. The expansion had slowed again. For several hours, the boundary remained nearly stationary along the southern industrial boulevard. Engineers used the pause to conduct additional experiments intended to characterize the altered electrical behavior inside the region. A series of controlled test circuits were assembled just beyond the perimeter. Copper loops, heating elements, electric motors, and semiconductor devices were connected to portable generators. One set of circuits remained outside the boundary. An identical set extended into the district. The comparison produced consistent results. Devices operating outside the circle functioned normally, converting electrical energy into motion, heat, or illumination. The circuits inside the zone displayed voltage across their terminals, but produced none of the expected effects. A motor inside the district accepted electrical input without rotating. ITS windings carried measurable current. The rotor remained perfectly still. One analyst proposed that the anomaly might have replaced the microscopic electrical interaction properties of materials within the region, altering how electrons transferred energy to atomic structures. In practical terms, electrical energy could move through conductors but could no longer perform work when encountering resistive or reactive components. The hypothesis aligned with the measurements, but it raised a new question. If electricity could no longer transfer energy inside the district, what happened to the energy entering the region through the grid? The answer appeared gradually as additional monitoring equipment was installed. Power entering the circle did not accumulate or dissipate as heat. Instead, the load on upstream transmission systems decreased. From the perspective of the regional grid, the district had effectively stopped consuming energy altogether. Electric potential existed. Energy transfer had been removed from the equation. Shortly after midday, another irregular observation emerged along the northern boundary of the circle. Engineers reviewing the perimeter sensors noticed that several test devices positioned close to the edge had briefly resumed normal operation before returning to their inactive state. The event lasted less than a minute. Field crews verified the readings by repeating the experiment. Portable heaters placed at the boundary line began producing heat while positioned just outside the district. When technicians pushed the devices several meters inward, the heating effect faded gradually before stopping entirely. But when the equipment was returned to the boundary again, the heat output resumed. The transition between normal and altered electrical behavior was not perfectly abrupt. A narrow transitional band existed where energy transfer weakened progressively. This discovery provided the first measurable structure within the phenomenon. The circle did not merely define a geometric absence of electrical function. It created a gradient zone where the interaction between electricity and matter diminished continuously before disappearing. While engineers studied this transition band, another development occurred within the city's monitoring infrastructure. Telecommunications providers reported signal amplification anomalies within the district. Cellular transmitters located inside the circle continued generating electromagnetic signals, but the devices themselves consumed almost no electrical power while operating. Under ordinary conditions, transmitting radio signals requires significant energy. Inside the district, the same signals were produced with negligible energy input. This observation forced a revision of the earlier hypothesis. Electrical energy entering devices inside the region was not simply failing to interact with materials. The interaction had been replaced by a different energy relationship. Electric potential still existed, but the conversion pathways between electrical energy and other physical processes had changed. Late that afternoon, the Grid Control Center detected a second expansion of the circle. The southern perimeter moved several dozen meters farther along the industrial corridor, placing a larger section of the transmission conduit inside the altered region. Yet the growth slowed again shortly afterward. This irregular pattern, periods of apparent stability followed by sudden movement, complicated attempts to predict how far the phenomenon might spread. Engineers developed models projecting potential expansion scenarios across the metropolitan grid. Several projections extended the circle beyond the city limits within weeks. Others suggested the growth might halt entirely. While the long-term behavior remained uncertain, the immediate operational response became clear. The grid could not rely on infrastructure located inside the region where electrical energy behaved differently. Utility authorities began implementing a permanent monitoring framework around the district. New sensor arrays were installed along the perimeter to track boundary movement and electrical interaction changes. Transmission routing models were updated to prevent heavy loads from crossing into the zone. Emergency power planning also changed. Hospitals and data centers near the district relocated backup generators to facilities positioned outside the boundary, with mechanical power transmitted inward through alternative systems where possible. In effect, the city began reorganizing its electrical infrastructure around the circle. Several weeks later, satellite imagery revealed that the region remained visible through its environmental consequences. Buildings inside the district emitted less heat during cold weather due to inactive heating systems. Traffic signals operated using mechanical timing devices installed after the outage began. Streetlights near the boundary marked the transition clearly. Why? On one side of the street, illumination. On the other, darkness. The circular district remained sharply defined. Expansion had slowed to nearly imperceptible levels, though minor boundary shifts continued to appear in the monitoring data. Engineers studying the phenomenon gradually accepted a new operational reality. The city contained a region where electricity still existed, but could no longer behave according to its normal physical rules. No equipment failure caused the change. No environmental factor explained it. The electrical infrastructure had simply become embedded within a different set of material interactions. Power continued flowing around the district through the surrounding grid, while the interior remained a zone where devices accepted electrical potential, yet performed no electrical work. Over time, residents living near the perimeter adapted to the unusual boundary. Businesses relocated outside the circle. Maintenance crews installed mechanical alternatives for systems that once relied on electric motors. Life reorganized around the geometry of the phenomenon. And along the southern industrial boulevard, the buried transmission corridor still carries electricity through cables that pass directly beneath the altered district. Current flows through those conductors every day. Yet inside the circular region above them, the same electricity cannot power a single light.